Welcome to the Notes on Imaginary Numbers. To begin, I'm going to start off with our CLO for today, our Content Language Objective. I'm going to read this aloud. While I do, think about what you think it means and what we're going to actually do in this lesson, because at the end, you're going to tell me what you think we're doing today. So students will be able to create, in writing, equivalent expressions using imaginary number properties and the following language: transition words, imaginary number, property, exponent, term, real number, distribute. So what do you think we're going to learn how to do today? So to begin, let's start with all those vocabulary that we saw. Down here, this is the language part. Transition words I'll explain at the end when we talk about the language. So we need to start with imaginary number. No, it's not one of your actual vocabulary words, because there's no real way to define it. An imaginary number just is. They exist. Someone came up with them. You can prove a ton of facts about them. They have their own special rules, and they are imaginary numbers. The imaginary number is signified by an I. The letter I means something's imaginary. So property is a vocabulary word. A property, properties of numbers are basically the rules of that thing. So a property of something are the rules of that thing, or how it behaves is another way to think about it. Here, I'll change the color. So that's the properties. So we're going to learn about all the properties of imaginary numbers, like all of their rules and how they behave. So with imaginary numbers, we'll have exponents. An exponent, remember, is a little number. Upper right-hand corner that tells you how many times to multiply a number to itself. So a quick little example would be, if I had 4 to the power of 2, that means I'm taking 4 and I'm timesing it to itself twice, and 4 times 4 becomes 16. So term in math just means a collection of numbers and letters. So anytime two terms are being multiplied together, like 3 is its own term and x is its own term. If I did 3 times x, I get something called 3x. And 3x is just one term now, because multiplying things together makes it become one term. So even, let's say, if I added a y, that's still just one term, because that y is getting multiplied on, because whenever it's side by side like this, it means they're getting multiplied together. So as long as you're multiplying, it's all one term, because multiplying things together makes it become one term. However, let's say I wanted to add something on, like a 2. Well, anything you add on is not part of the same term. A plus sign will separate terms. So this is one term, and this is one term. A minus sign also separates terms. So this is one type of term. This is one term, and this is another term. We call terms their names based on their letters. So this one would be called an XY term. There's 3 XYs right here, but it's called an XY term. This plus 2 has no letters, so it's called a just number term. So this is a just number term. This term is an X term. There are many other types of terms. There's thousands. We could have, for example, a y cubed term. And that's its own type of term, which is different than, let's say, if I had 5y squareds. So the type of term here is a y squared term, but there happens to be 5 of them. So the term type is the letters that you see, the variables. And then how many you have is the number in front. So this whole little expression I have right here, I'll get rid of this front part. This now has one term right here, another one right here. Here's the third term. The x is the third one. The y cubed is the fourth term. And then the y squared is the fifth term. So there's 5 terms right now. If I multiply this to z, that's still a part of just that last term, that fifth term. But then let's say I wanted to minus 3z's. Now this minus 3z is its own separate term. So it's called its own term when there are numbers and variables. Number variable just means letter. Being multiplied together with no plus or minus sign separating them. Oh, quickly, I should note that multiplying and dividing are the same thing, because dividing just means multiplying by a fraction. If that confuses you, go watch the multiplying video in skill building. So that means that, let's say I have 3 xy's on top, and I'm dividing it by a z. This is not 2 different terms, because dividing is just like multiplying, where it's a part of the same term. This is one term. To make it a new term, I would have to add or subtract something. Like if I subtract 3. Now this is its own term, and this is its own term. So remember, there are imaginary numbers, and they are known as I. It is just a thing. Yeah. They're imaginary because they don't exist in the real world. So if I jump back to the CLO, I've talked about almost all of my vocabulary words: imaginary number, property, exponent, term. Next would be a real number. A real number is a number that you find in real life. Like, for example, I could have 2 apples, and I'd say, I have 2 apples. In an imaginary world, it doesn't exist in real life. It only exists in the imaginary world. And there's a whole type of math. Like, you can take a whole type of math class where you explore the imaginary world and how numbers work in the imaginary world. And they follow their own set of rules. And I'm going to teach you some of those rules about the imaginary world. However, if a number exists in the imaginary world, like, for example, if I said I have 2 apples, it would be saying I have 2 imaginary apples. So maybe it's in my head and it's not actually real. Yeah. I know this is a little confusing, but just believe me when I say imaginary numbers exist. You have to be able to play with them, and they follow some rules. Well, most of those rules are the exact same as the real world. So that's nice. So if I have I plus I, think of it like x's. If I have x plus x, that would mean I have 2 x's. So I plus I means I have 2 i's. So if I have one imaginary number here plus another imaginary number, I have 2 imaginary numbers. So it's super simple. It's just like if it was like an x, except we're using I. So here, if I have 7 imaginary numbers, 7 i's, and I'm minusing 2 imaginary numbers, how many imaginary numbers do I have left? I have 5 i's, 5 imaginary numbers. So here's a property of I that's very similar to the real world. You cannot combine imaginary numbers with real numbers. So here I could combine them because they were both i's. They're both imaginary. These are different terms. This is an imaginary term. This is a real life term. Because they don't have the same letter next to it, because this is imaginary, I cannot put them together. So if I was told to simplify this, as weird as this is, the answer is just 1 I minus 3. Because they're different terms, they cannot go together. So I times I works just like x's. So x times x would be x squared. So I times I would be just I squared. So this is another way that imaginaries work just like real numbers. However, the next one is the one rule that makes everything different about imaginary numbers. With imaginary numbers, I squared is -1. That's just the thing about imaginary numbers. The reason why they're imaginary is because they needed to come up with this rule where the imaginary number squared, I times I, is -1. Yeah, that's just the answer. So let's practice a few to see what the heck I mean. So if I have 3i to the power of 5, that means I have 3 times I 5 times. So times, there's a second one, third, fourth, fifth. But for every I times I, like this, I can combine them. I times I was I squared. Meaning, 3, this I times I is going to combine into 1, -1. Because I times I is -1. That's the rule for imaginary numbers. The next I times I will also combine and turn into a -1. This last I is alone. It doesn't have 1 to combine with. So I just write I at the end. So now to finish my math up, 3 times -1 is -3. Times -1 again goes back to being +3. And then this I is at the end. So if I was told to take this and simplify it to write an equivalent expression that's the same, but simpler, 3i is the same as 3i to the power of 5 because of this rule right here. Let's do another one. So 2 times I squared means what? What can I replace I squared with? So I squared is I times I, and then I still have a -5. But remember, every I times I can be replaced, or just at the I squared step, you could have replaced it with the fact that it's the same thing as -1. So now, when I finish this up, 2 times -1 is -2. -5 becomes -7. So let's talk about the differences between these two. Here, if I added something at the end, like a +1, and I had a +1 at the end of all of this, I could not combine the 3i with the +1. This would just be my answer because I cannot combine imaginaries with real numbers. But that +1's not there, so let me get rid of it. However, in this one, my imaginary numbers, once simplified into the -1, there were no more i's left, meaning this stopped being imaginary. It went from being imaginary to being real. This is a real -2 because the i's went away, which means I can go from the imaginary world to the real world sometimes, depending on how many i's I have. Because this time, because I had 2 i's, they combined and they went away, and there is no more imaginary. Over here, when I had 5 i's, when I combined the ones I could, I was still left with an I. So I still ended up in the imaginary world as my final answer. Versus on this one, my final answer went to the real world because the imaginary numbers went away. This time around, this looks a different. These types of questions look different than these types. These types, there is no math to do before simplifying my imaginary numbers. It was like my first step was, all right, I have i's, let's write them out, change these into real numbers and simplify back together. Here, to combine these, I'm stuck because there is a parentheses with a minus sign in front of it. So because of that, I cannot put anything together yet. What it means when there is something right in front of a parentheses is it means you need to multiply that thing inside everything in the parentheses. So first I have to take this negative sign and multiply it to the two things in the parentheses after it. Not before, that's before it. But the thing right in front of it, being the negative, needs to go into both things in the parentheses. So when I do that, I still have this 6i and the minus 5. Then when I times the negative to the 3, I get what? Negative 3. And then they're i's, because there's an I on that one. And when I do negative times positive 4, what do I get? Minus 4. So now, if I look, this parentheses, why is it here? Well, in the original problem, it was here so that you knew it was separate from this minus sign. But once I get to this step, the minus sign already went in to both. So I did that. Usually parentheses, if there's something in front, I would multiply it in, but there's not. If I could combine these two, I would have to do that first, but I can't combine imaginaries with real numbers. So I don't need this parentheses anymore. Now looking at this, I just have to put my things that are the same together. For example, I have these 6 i's. Do I have any more i's later on? I do. Right here I have minus 3 i's. So I'm going to put those by my 6 i's and combine those two together. Then if I take my just number term, do I have any more just number terms? Yes, this minus 4 later on. Now I can combine like terms, the ones that are the same. So I could do 6i minus 3i's. How many i's am I left with? I'm left with 3 i's. And then if I combine my just number terms, minus 5 minus 4. You owe me 5, you owe me 4. Are you going to have money or owe me? And how much? You're going to owe me 9. So then this expression up here is equivalent to this one. They're the same thing. I just simplified it. I used all my properties of I, put it together and simplified. I have to do the same thing for this one now. This one's a little bit different because there's nothing in front of this parentheses, like no other number, no plus or minus. What's in front of it is a whole nother parentheses. And so that means I have to take this whole first parentheses and multiply it to the whole second parentheses. Hopefully you remember the notes on distribution or multiplying polynomials. But if not, I'm going to quickly run through the rules. If you're confused, talk to me about it so I can help teach you it and remind you. But here's basically how it works. Every term in the first one has to be multiplied to every term in the second one. Then we simplify everything out after that. Which means I have to take this I, this first term, and multiply it to the 4i and to the negative 7. Because I have to take the first one and multiply it to both in the second one. So then once I've done that, I times 4i is 4i squared. And then I times negative 7 is negative 7i. So we've done the first term into both in the second. But I also have in my first parentheses this plus 3. So this one has to get multiplied to both terms in the second parenthesis as well. So when I do the plus 3 times 4i, well, what do I get? Plus 12i. And when I take the plus 3 and multiply it to the negative 7, what do I get? Negative 21. All right. So my next step, I have 2 choices. Doesn't matter which one you take care of first. So there's the fact that I have an I squared. And because it's imaginary, I'm going to want to replace that I squared with a -1. So anytime I see imaginary numbers with exponents, I should try to write it out. The I squared would just be I times I. And I times I is just -1. But if you had more than a 2 up there, then you'd want to write them out so you figured out how many -1s you have and how many i's you'd have left, so on and so forth. Then also, my next thing, so I could make that my first step, so I'm going to. So then I'm just going to copy the rest. I didn't have to start with this step, but since I did, I'm going to combine 4 times -1. And 4 times -1 is -4. And then I should copy down everything else I have. And now that I've done that, I can combine like terms that I have. So, for example, in the middle, I have -7i plus 12i. So if you are down 7, if you owe me $7, but then you get 12, once you pay me off, are you going to have or owe money? You're going to have some money still. You're going to still have $5. But remember, these weren't dollars, they were imaginary numbers. So I combined the -7 plus 12 to a positive 5i. I also can combine this -4 with the -21 because those are both just numbers terms. So it's okay if I take this -4, get rid of it from there, and put it at the end next to that 21, the -21. Since this is a +5, but it's starting the sentence, I don't have to write +5 anymore. It just means positive 5. When I combine these two, -21 minus 4 is 21, and then you owe me 4. You're going to end up owing me 25. So this long expression right here, at the very beginning, after distributing it out, meaning multiplying everything out, and then combining like terms, and then using my properties of I have simplified it to this expression. So there's a whole part on the test where you have to take expressions like this that are imaginary expressions and then do some math to simplify it into an easier imaginary expression, or sometimes even into a real one if we end up getting rid of the i's. This is not the only reason why we have imaginary numbers, though. They end up being way more important to us for other reasons besides their properties and rewriting things. One reason they're important is because they show up with the radicals that we were dealing with yesterday. So if you remember, the last lesson, the square root of 4, the first step to figure out the answer would be to break that 4 apart into prime numbers. So when I break 4 apart into a list of prime numbers being multiplied together, what's the answer? It becomes 2 times 2. And then remember, if it's under there twice, it can come out of the square root just once. And then I still have to put the square root of what's left inside, but both of those came out, so there's nothing left inside. And if there's nothing left inside, I don't need that. So the answer is 2. The square root of 4 is 2, because 2 times 2 is 4. However, that is not the only answer. Because tricky, -2 times -2 is also positive 4. So technically, anytime you simplify a radical, the answer isn't just 2, it's also -2. So there's this symbol in math that looks like this. Here, I'm going to zoom real fast. If you look, it's a plus and a minus. That's the quick way to write 2 answers. It's the quick way to write this 2 and -2. Instead of having to write both of those, you can just write this little plus-minus symbol. So technically, on that worksheet that you did yesterday, if I was being very stingy, all of your answers would have been wrong if you didn't put the plus-minus in front of all of your answers. However, I don't really care on that worksheet. But I am going to care from now on. So whenever you take the square root of something, whatever your answer is, it is both the positive and the negative version of it. Because a negative times a negative is always positive. So that fact matters a lot. A positive number times a positive number equals a positive. A negative times a negative is also a positive, right? So that means if I take the square root of something, like if I take the square root of a positive number, the answer gets to be both positive and negative. So the answer is positive and negative. Whatever the answer is, it's going to be both positive and negative because they could both show up under that square root. So then, what if I try to take the square root of a negative? Like, what's the square root of -4? Just guess, what do you think the square root of -4 is? So the answer can't be 2. It's not 2. Because 2 times 2 is positive 4. Also, it's not -2. Because -2 times -2 is also positive 4. So what's negative? The square root of -4. What times itself is going to be -4? Is there any number, when you multiply it to itself, that the outcome is going to end up being a negative number? There is. We were just talking about it. It's I. Yes, it's the imaginary number I, because only I times I. It's the only thing in the world. The imaginary number I times the imaginary number I becomes -1. All the real numbers, when you square them, if it's a positive real number, it becomes positive. If it's a negative real number, when it's squared, it still becomes positive. Only the imaginary number, when squared, equals a -1, which means the only way to take the square root of a negative is if we have i's in it. So the square root of -4 is the same thing. If I split apart 4, 4 becomes 2 times 2. But for it to be a -4, there needs to be a -1 in front. So if I were to split apart 4, it would become 2 times 2 times -1. So anything that's under the square root twice can come out. But remember, -1, if I go into imaginary numbers, -1 is the same thing as I times I. Because I times I is -1. That's the rule we're learning today. See up here, I times I is -1. So this I times I is the same thing as -1. Which means -4, when split apart, turns into I times 2 times 2. So if it's under there twice, it can come out. So the 2 can come out as 1. The I can also come out as 1. And then under the square root, well, everything's come out. There's nothing left in there, so I don't need the square root. So the answer to the square root of -4 is 2i. Well, not just 2i. Because remember, it's always the positive and negative version. So you could write like that, or you could say 2i and -2i. These mean the same thing if you write plus minus, or if you write it out the long way. So let's do some examples. So the negative can always split away from the number by dividing by -1. I'll show you. If I have -50 like this, and I divide it by -1 and press equal, the answer becomes +50. So by dividing out that -1, I'm left with 50. My next step, if I try dividing 50 by, what's the first thing I divide by? 2, I get 2 and 25. So this 50 can turn in the 2 times 25. 25 is not a prime number because it's not on the prime number list when you go into my tools. So 23, 29, it skips 25. So I can divide 25 by something. If I try by 2, it will not work. If I try by 3, I will also get a decimal. I don't try 4 because it's not a prime number. I try dividing it by 5 next, and I find out that 25 is 5 times 5. So I can replace this 25 with 5. It's 5. But here's the thing, 5 is a prime number. So I know that this one's done. It doesn't need to be split apart anymore. And now it's all in prime numbers. Almost. We're almost done splitting it up because remember, we always are going to want to split the -1 up into 2 i's. So now if it's under there twice, it can come out front. So these 2 5s at the end can come out front. These 2 i's at the beginning get to come out front. But under the square root, I'm still left with that 1, 2 right here because it didn't have anyone to combine with. So this here simplifies to this almost because we have to remember and the negative version. Remember, I could have written this. The quicker way would have been if I just did plus minus 5i root 2. All right, for the next one, first step is I want to divide out that -1, so I'm left with positive 162. I take 162 and try to divide it by 2, and it works. I get 81. Take the 81, try to divide it up. If I divide it by 2, I get a decimal. But if I divide it by 3, I get 27. So it becomes 3 and 7. Next, I'm going to see if I can divide this 27 up. If I divide it by 2, I'll get a decimal, but when I divide it by 3, I get 9. 27 times 3 times 9. Now I want to see if I can divide this 9. What is 9 split apart into? 9 can become 3 times 3. And then my last step is I have to divide -1 into what? Remember, -1 becomes I times I. And if it's under there twice, I could break it out front once. So I see 2 i's right here. One of them can come out. They combine as one and come out as one. This 2 doesn't have a partner, so it's still left underneath. These 2 3s can combine and come out front one time. These 2 3s can combine and come out front one time. And then there's no more 3s left underneath. So then when I finish up this answer, well, first going to be a plus minus because I took a square root. Then I do 3 times 3 back together to get 9. Then I have the I. And then left under the square root, I just have a 2 with nothing to multiply to. So then that's my final answer. All right, square root of negative 36. What does negative 36 break into? Skipping all of the steps, the negative 1 should become an I times an I. 36 divides into 2 times 2 times 3 times 3. So if it's under there twice, it can come out front. So here's 2 I's that can come out front. Here's 2 2's that can come out front once. There's 2 3's that I can combine and come out front once. Is there anything else left under the square root? No, there's not, so I don't need to write it. My final step would be just combining these together. So 2 times 3 becomes 6, and then you just write the I at the end, because you always write the number first, then the letter. So instead of I6, you're going to want to write 6, then I. There is no square root, but then I can't forget that this is a plus minus. So positive 6i and negative 6i is the answer to the square root of negative 36. So going back to our CLO, you're going to want to use transition words to explain to me what we did today. Try to give me a step-by-step guide. Transition words, here, let me explain it, are ways how we move from one thought to another. So if I'm thinking of like, I like apples, I like bananas. This sentence, or these 2 sentences, could become one sentence if I used a transition word. So one idea of a transition word would be and. And is a way we transition from thoughts. So I could say, I like apples and I like bananas. Or I could just say, and bananas. So what transition words do is it can let you combine thoughts together into one sentence and make more unique sentences. Another transition word, let's say instead of saying I like apples, I like bananas, I want to say I like apples, I don't like bananas. Well, a transition word to combine those 2 thoughts might be but or however. Because I could say I like apples but not bananas, or I could say I like apples, however, not bananas, and it will mean the same thing. More transition words for thoughts that connect to each other. Like I might want to say, I like apples, I eat one every day. A way to connect those sentences with a transition word might be so, because I could say, I like apples, so I eat one every day. Another transition word for connecting thoughts that go together is therefore. So I like apples, therefore I eat one every day. So these are tons of transition words to make sentences more interesting, and we use them a lot in math. So go ahead and use transition words to explain along with these vocabulary words to explain what you learned in this lesson.